Okay, hi again. Okay, assalamualaikum. Alright, this will be the last slide for part 1. Before we maybe on next I will post on the part 2 for buck converter. Okay, so where do we stop just now? Alright, okay. So in order for us to do the analysis with regards to DC to DC converter in finding the voltage and the current for DC to DC converter, okay, we will focus on the CCM first, which is continuous conduction mode. Okay, so we need to have some assumptions in order to ease the analysis. So first is that we assume the inductor current is always continuous, which means that your inductor current, your IL, will have a positive value. So your IL will always be continuous. Okay, that is one of the assumption. So by mean of always continuous, in either switch operation, whether the switch is on or the switch is off, the current must always be positive. Okay, the second assumption is that we assume the average inductor current and average inductor voltage and average capacitor current are 0. So average VL equals to 0, and also average capacitor current equals to 0. Okay, so we have these two assumptions. Okay, and then we assume all components are ideal. So all components are ideal by mean of this is that there will be no losses contributed by each of the component inside the circuit. So your input power will be equals to your output power. Okay, so these are the three assumptions that we make in order to ease our analysis in CCM. Okay, so we know that when your switch is on, okay, your diode will become reverse bias and you will have a positive output voltage. Okay, so it will also result a positive inductor voltage. Okay, alright, so these are the voltage analysis and the current analysis with regards to the first equivalent circuit when your switch is on. Okay, let me draw it so that you'll be able to get more understanding on how to get all this equation over here. Okay, and also later in the slide. Okay, and this is when the referring to the second equivalent circuit. Okay, this is referred to second equivalent circuit, yeah. Okay, so when your switch is off, this is when your diode will become fault biased and it will conduct the inductor current. Okay, and these are the analysis of the voltage and current. Okay, so let us draw. Okay, we refer to the first equivalent circuit. When your switch is on, your diode will become reverse bias. Okay, so from the circuit just now, we have your DC input. Okay, then you have your switch here. Okay, and okay, Vs, this is your switch, and this is your diode. Your diode become reverse bias, so it will act like an open circuit, and then you have your inductor, your capacitor. Okay, remember, your capacitor must always be connected in parallel with your load. Okay, okay, I not here, and okay, we have I, right. So this is the equivalent circuit. From the assumption just now, it mentioned that the average capacitor current we assume to be equals to 0. So you can get rid of the path that that associate with the capacitor. So we get rid of this. So let's say we redraw it again. So your input, then you have your switch here. So since your diode is open circuit, so you can just assume that there is no diode there. Then okay. Alright, so this is how the current flow from the input to your output. Okay, from this equivalent circuit, you can see that, okay, let's say we start with the voltage across inductor, the analysis for the voltage across inductor. So we applying the KVL, Kirchhoff voltage law. Voltage across inductor will be equals to your output voltage. Nope. Okay, your voltage across inductor will be equals to your output voltage minus your input voltage Vs. Okay, we know that the summation of all current, if let's say we refer to the KVL, summation of all voltage will be equals to 0. Okay, and then we define this voltage across inductor by using Ohm's law, V equals to IR. Okay, so since voltage across inductor VL is associated with inductor, so our R will become L. So L DIL over dt. Okay, right, will be equals to Vs minus, sorry, V0 minus Vs. Okay, this L di over dt is also can be represented by mean of L delta IL over delta T equals to V0 over minus Vs. Okay, then we bring the inductor to the other side, so delta IL over delta T will be equals to V0 minus Vs over L. Okay, delta T over here is the duration of your turn on time, which is, if you are referring to the what we call this, the waveform, the output waveform here, this one here. So we know that this is when your switch is on. So now we are doing the analysis when your switch is on. This is when your switch is off. Okay, so this delta T here, sorry, the T on here will be equals to dt. Okay, so you replace your delta T here with dt. So your delta IL will be equals to V0 minus Vs over L. multiply by dt. So you get your first analysis, okay, with regards to the delta IL. So this delta IL, which means that the changes between the maximum and the minimum of your inductor current. Okay, delta, which means the changes of minimums and maximum and minimum. Yeah. Okay, so you get the first equation. Okay, say I denote as 1. Okay, now we go when your switch is off. Okay, this is when your diode will become forward bias. Okay, let's say we draw the equivalent circuit again. Okay, so off here, your switch is off. Okay, we have the inductor and I removed the capacitor here. Okay, because of the assumption, we assume your capacitor current equals to 0. And okay, from this circuit over here, you notice that the switch here is open circuit. Okay, it's open circuit. So which means that your VS will not be connected with your circuit over here. Okay, so you can get rid of this part here. So we redraw it again. So it will become like this. Okay, your diode here, and you have your inductor and your load over here. Okay. Alright. Okay, and then you need to okay, and then when we have this one over here, okay, we need to perform the analysis in finding the voltage and the current for the when the switch is off. Okay, so we start similar to what we did during the analysis when switch is on. So your VL will be equals to V0 minus Vs. Yeah. Okay. Oh, sorry. I got it wrong. It should be Vs minus V0. Okay. So since in this analysis, your Vs is being disconnected from the circuit, so which means that your Vs here will be equals to 0. So your voltage across your inductor will be equals to negative V0. Okay. Alright. And then we replace our VL with element of inductor and current. So which is L DIL over dt equals to negative V0. Okay, and then we replace your di over dt with delta IL over delta t equals to negative V0. Right, and then we know that this is when turn off time. This is when your switch is off, which is equals to 1 minus t times t. So it will finally you will get this equation, delta IL when your switch is off will be equals to V0 over L multiplied by 1 minus t times t. So I name it as equation number 2. So you have these two equations. Okay, from these two equations here, you need to sum up these two equations by using KCL, Kirchhoff current law, in order to find the equation for the duty cycle. Okay, so by KCL, so delta IL when your switch is on plus delta IL when your switch is off equals to 0. Okay, alright, so we have delta IL, which is Vs minus V0 over L, so multiply by dt. Then you have this delta IL when your switch is off, which is negative V0 over L multiplied by 1 minus t times t equals to 0. So Vs over minus V0 over L dt. So we bring VL to the side. V0 over L 1 minus t times t. Okay, these two VL okay, t over L here, Vs minus V0 d okay, and then t over L V0, so t and dt here, so wait, okay, so t dt, so we bring out the t there, so it will become zd. You bring up V0 t V0 d, is it right? V0 t minus vdt, yeah. Okay, so this t here can be cancelled out. Okay, and then you will then you will have Vs d minus V0 d, so minus Vd plus V0 d equals to 0. So you cancel out this bit over here. Okay, and then from here you have V. Alright, you have this bit over here. Alright, so you have Vsd minus V0 equals to 0. So you bring out V0 to the other side. So your duty cycle will be equals to V0 over Vs. So this is how you should get your duty cycle. Okay, this is for buck converter. If let's say that for another type of DC to DC converter, the way what we call the equation in finding the duty ratio will be different. Okay, it depends on how the position of the switch, diode and inverter will be. Right, okay, so from this from the slide here you can see that, okay, I already write down how we get this equation over here. Right, okay, and then so your duty cycle for buck converter will be equals to Vs minus V0 minus Vs, your output voltage over your input voltage. Okay, and then okay, this is how the what we call the derivation in order to prove that the average inductor voltage is equals to 0. Okay, you can have a look on here and try to integrate this in order to get 0 here. Okay, all right. Okay, so we know that with regards to the equation of duty ratio, you can see that the duty ratio for buck converter is only affected by the amplitude of your output voltage V0 and also the amplitude of your input voltage Vs. It does not affected by the value of your inductor, by the value of your capacitor in the circuit. Okay, so from here we can assume we can make a conclusion that the output voltage only varies, okay, linearly with duty ratio, okay, of the switch for a given input voltage. Okay, in this sentence it means that if let's say that your Vs is fixed, okay, so which means that when your duty ratio is increased, your output voltage will also increase. Okay, so this is meant by this sentence over here. All right, so the duty ratio generation does not depends on any other value or parameter in the circuit. All right, okay, so that is basically on how to generate the equation of the duty ratio. Okay, next I will proceed on the analysis in finding the passive the value of the passive components in the buck converter, which is the value of inductor and the value for the capacitor. All right, okay, so we will I will see you guys sorry, we are not I will see you, I will record it for the next one. All right, okay, till then, okay, take care, stay safe, okay, stay at home.